The Experimental Boiling Water Reactor is a direct steam cycle nuclear power plant located at Argonne National Laboratory near Chicago. The reactor and power components are housed in a steel containment shell 80 feet in diameter and 120 feet high, half of which is below ground level. The attached brick building accommodates plant control equipment and offices. After placement of the reactor pressure vessel and other units of the steam system is complete, the installation of reactor components begins. A 1-inch thermal shield of 1% boron stainless steel is assembled around the core region. A lighter stainless steel shock shield located above the thermal shield protects the vessel walls from cold boric acid water spray. This assembly will guide control rod extensions into thimbles extending through the biological shield beneath the reactor. The core structure, without fuel, is assembled on the core grid plate. Within the active core assembly, the structure is zirconium, and that portion above the core, including the outer shroud, is stainless steel. In the initial assembly, an outer ring of aluminum dummy elements completely fills the support plate holes not occupied by active fuel assemblies. These spaces can be made available for extending the diameter of the core. The natural circulation of water in the reactor is up through the fuel assemblies and down through the reflector, providing a path around the periphery of the core. Control rods are fitted to obtain the best alignment. 5 of the 9 rods are made of hafnium, and the 4 corner rods of 2% boron stainless steel. An indexing carrier assembly permits alignment of the access port with any of the 148 fuel assembly positions in the core grid plate. Fuel assemblies weighing 160 pounds are handled with a cable crane. The latching device is so designed that when it carries weight, it cannot be released. Variables available for controlling performance in the reactor are enrichment of fuel and thickness of fuel plates. During the series of pre-operational experiments, the assemblies with thin elements are loaded in the center of the core, permitting over-moderation of this region to minimize the effect of voids on reactivity. A close check on neutron flux is maintained as each fuel element is lowered. For all pre-operational experiments, the building is completely cleared of personnel and the doors secured. A first critical loading of 88 assemblies was established by a series of experiments run in the reactor. 60 pre-operational tests, each requiring approximately 1 hour, were performed to correlate and check the physics of the core with calculated performance. These tests were completed by December 23, 1956. The loading for 20 megawatt operation was established at 114 fuel assemblies, most of which contain 1.44% of the uranium-235 isotope. The top of the reactor vessel is bolted into place. With the upper shield ring positioned, steel wool in aluminum containers is placed over the bolts. A water tank suspended from a 6-inch thick steel plate completes the upper shield. Hold-down beams attached to vertical columns provide additional safety. In the event of an explosion in the core, the force would be expended downward, preventing rupture of the containment shell. Preparations complete and the building cleared, all control rods are driven in a bank to about 19 of their possible 47 inches of travel. At 19 inches, the reactor produces 20 megawatts of heat for the first time. The small back and forth movement of the pen is about 4% of the total power reading. The reactor pressure is 600 pounds per square inch. With the reactor at 20 megawatts of heat and the steam being bypassed to the condenser, the first generation of electrical power is undertaken. The generator is synchronized. The steam flow, normally 60,000 pounds per hour, varies as pressure changes are felt by the steam flow controls at the turbine. The objective of 5,000 kilowatts electrical is attained about 1 hour after the full design power of the reactor is reached, December 29, 1956. A period of plant checkout followed, during which a number of operators were trained to run the EBWR on a routine basis. Normal shift consists of a 4-man crew. Before startup, the instruments that monitor reactor flux are inspected to see that all of them are properly adjusted. The startup heater, utilizing steam from the laboratory's process line, increases the reactor water temperature to 325 degrees Fahrenheit. An interlock prevents control rod operation until preheating is complete. The missile shield protecting the main entrance door is closed. Inspection of the high-pressure boric acid system completes the pre-operational plant check. This concentrated boric acid solution would be injected into the reactor if, for any reason, control by rods was lost. Personnel leave the building through the double-door main airlock. These doors permit access to and from the plant during operation without breaking the integrity of the containment shell. In the control room, control rod insertions are timed to assure that each moves freely. The high condenser pressure and turbine trip valve shutdown interlocks, which cannot be cleared at startup, are bypassed with key switches. Later, the switches will be opened so that a total of 15 protective circuits function. Before the operator begins to raise the control rods, he records a counting rate as a base or starting point. The rods are raised 6 inches, one at a time. At this point, a new counting rate is compared with the base rate, measured with rods all in. If the new rate is steady and normal, the rods are raised to 10 inches, then to 12, and finally to 14 inches. From the history of this reactor's operation, it is known that the reactor will be critical when the rods are raised approximately 14 inches. The center rod is left somewhat lower than 14 inches to transfer control to that rod. This simplifies the procedure for setting the startup period. The pen is beginning to move up scale, and the operator is trying to obtain the 30 to 40 second period. The power the reactor will reach and control itself when it is started with this period has been established from previous experiments. Having obtained the period, the operator simply observes the flux rise. No rods are moved during the next few minutes. Scale changes to follow the flux increase are noted on the chart. Pen movement to the right indicates an exponential with about a 30-second period. The return movement to the left is due to changes in scale. At about 100 kilowatts, the heating of the core lengthens the period, and the last rise is nearly a straight line, far from being exponential. This demonstrates the unique ability of the boiling reactor to nullify a period and to control itself. At 750 kilowatts, the pen has begun a cyclic variation. The flux falls, then rises, completing the cycle in about 15 seconds. This is typical of a low-pressure startup. This variation at the inception of boiling is not particularly disturbing when recognized. It is attributed to the heating of the water, which then begins to flow over the upper shroud and down through the reflector, disturbing both flux and reactivity. This variation is rather large at the present time, 20% of the total reading. After a few minutes, the magnitude of the variation has decreased, and so has the average flux. This flux fall continues, but the operator waits until the signal is relatively smooth before withdrawing the rods further. The reactor was started with a 30-second period. It eliminated that period, and the reactor is self-controlled at about 300 kilowatts. With all steam lines closed, the pressure increases as a result of heating. At 150 pounds, the flux variation has decreased noticeably. The rods are then driven out to raise the power to 1 megawatt. This 1 megawatt reference value for startup was established as that power which would give the proper heating rate to the reactor pressure vessel. Every minute or two, rods are moved a fraction of an inch to maintain the flux at the desired 1 megawatt value for heating. During the startup process, when steam flow is zero, the addition of cold feed water injects positive reactivity in the reactor, causing a rise in flux to a new equilibrium point. When the feed water is turned off, the flux returns to the previous level. This demonstrates the sensitivity of the reactor to changes in feed water flow. At 300 pounds pressure, steam is applied to the turbine gland seals. The steam jet air ejectors are energized to start evacuating air from the condenser. Circulating water pumps for the condenser and the cooling tower fans are started to establish the heat removal system. By the time the pressure in the reactor has increased to 600 pounds, the vacuum in the condenser will be at 25 inches of mercury, and the turbine will be heated and ready to accept the load. The loading of the steam system causes the flux to fall. Reactivity decreases, and the reactor power falls toward a new equilibrium. The reactor again is self-controlling. With the condenser vacuum at 25 inches, the operator withdraws the control rods to increase the reactor power. It takes only a few minutes to obtain 20 megawatts. The pressure rise between 500 and 600 pounds produces very little temperature rise, and the power is increased at will. At 600 pounds, the bypass valve passes steam directly to the condenser, causing the reactor water level to fall. The water level controls are then put on automatic. The demand for steam at the bypass valve causes the same loading effect as was noticed before. The flux falls rapidly as the steam begins to pass through the lines, and the drop is the result of opening the bypass valve. The instrument scales are changed after the flux drops to center the pen. Feed water is being injected automatically, giving an additional rise in flux. The rods are withdrawn until the steam flow is up to 60,000 pounds per hour, using flux as a limiting guide. This chart is typical of the flux indication throughout the entire power run. The turbine generator is then brought up to its rated speed of 3,600 revolutions per minute. The synchroscope is turned on and the fine adjustment of speed is made. The generator is synchronized, and the output increased by adjusting the turbine admission valves. Opening the turbine admission valves automatically adjusts the bypass valve to maintain a constant steam flow. As the bypass valve closes, the bypass steam flow meter on the left shows a decrease. At 5,000 kilowatts electrical, the bypass steam flow is 0. With the entire plant in normal operation, a routine inspection of all plant equipment is made, starting on the main floor with the 5,000 kilowatt turbine generator. A special feature of this turbine is the labyrinth shaft seals to keep steam from leaking out and air from being drawn in. Air monitoring equipment, just this side of the generator, collects any radioactive particulate matter in the air. Filter papers from these monitors, counted at regular intervals throughout the day, indicate a radiation level only slightly higher than background. On the floor below, the steam bypass valve makes possible reactor operation independent of the turbine. The air ejectors remove non-condensable gases from the condenser. These gases are monitored for fission products as a means of detecting a fuel element rupture. Across the aisle at the face of the reactor shield are the water level sight glass and feed water valves. Moisture collected by the steam dryer passes through a steam trap to the condenser, and dry steam is piped directly to the turbine and bypass valve. All water from the condenser passes through the main full flow filters before returning to the reactor. The condenser has a divided water box. In case of a leak, the faulty half can be shut down and the reactor heat removed by the other half. Two pumps circulate a total of 14,000 gallons per minute of cooling water through the condenser and over the cooling tower. The fluid recovery system is located on the third level. Dry air is fed to chambers around each turbine shaft seal. Gland steam and some of the dry air are returned to this system where moisture is recovered. The system was designed particularly for future operation with heavy water. For 20 megawatt operation, a 150 horsepower feed water pump returns condensate from the hot well to the reactor. The additional pump is provided as a standby measure. The shield cooling system is monitored for both temperature and flow, cooling the shield that surrounds the enclosure for the reactor pressure vessel. Retention tanks on the bottom floor collect all liquid waste for radiation monitoring before being pumped out of the building. In the side stream purification system, reactor water circulates at 8 gallons per minute through a 9 cubic foot mixed bed resin column. The resistivity of the reactor water is maintained at more than 1 megohm. When the resin is depleted, the shielded containers can be removed from the plant for replacement of resin. The last stop in the tour of inspection is the underside of the reactor proper. Control rod drives and seals are thoroughly checked. The drives are attached to the bottom of the control rods through labyrinth seals, which were used for the first time on this reactor. A roller latch carriage engaged with a lead screw permits movement of the control rods in either direction by the drive motors. Having completed an inspection of the building, the operators return to the main floor some 50 feet above. This routine inspection is made at least once during each shift. Access to the plant during operation is completely safe, since the radioactivity is low and does not present a hazard. The initial operational phases of the Experimental Boiling Water Reactor established that the direct boiling cycle nuclear power plant was completely practical for operating a generator in parallel with a utility network. The engineering test data taken during operation included many disciplines. Particularly significant data is obtained by measuring the effect of a known reactivity variation on flux. The center control rod drive mechanism is modified to permit a sinusoidal reactivity variation. The reactivity disturbance and resulting output flux are recorded and analyzed to determine the relationship of phase and amplitude between input and output. Accuracy of the experiment is 5% in amplitude and 2 degrees in phase. These transfer function measurements indicate reactor stability to 65 megawatts and possibly as high as 85 megawatts. Operating confirmation of these predicted high power capabilities are then undertaken. A transient reactivity response is used to indicate qualitative stability rather than transfer function measurements. First, the power is raised to 30 megawatts and a step reactivity disturbance of 0.1% positive was inserted. A decaying transient occurred, indicating that the system was damped and completely stable. Increased to 40 megawatts, the stability test is repeated. The flux response indicates the predicted stability at this power. Following the same procedure, the power is brought to the objective of 50 megawatts with the original 114 element core. After intermittent turbine operation totaling 3,060 megawatt days, the customary first-year inspection is made. Although reactor steam is fed directly to the turbine, maximum radiation activity upon opening the turbine is found to be 2 MR per hour on internal surfaces, with the exception of the steam chest, which is 5 MR per hour. Radiation problems in connection with maintenance are negligible. The turbine is in excellent condition. Surface scrapings of the turbine blades are made for detailed analysis. The reactor core is examined for flux distribution by determining the gamma activity from fission products. To obtain a plot of the flux, an element is raised above the core and tubes containing ferric sulfate lowered along the side of the element. From these measurements, the ratio of maximum to average neutron flux is calculated to be approximately 3:1. Irradiated elements are removed from the reactor by means of a coffin to shield the operators during the transfer. With the indexing plug rotated into position and the transfer coffin aligned with the port, the element is latched and drawn up into the coffin. When the coffin is closed, it can be filled with water to assist in cooling the element. Rolled to the adjacent storage area and the water drained, the element is lowered into a slot from which the transfer proceeds with regular fuel handling tools. The element is visually located in the storage crate. This element, scheduled for metallurgical and chemical examination, was replaced in the reactor by a new fuel assembly. A change in core loading was planned to permit higher power operation. Two enriched fuel assemblies from the periphery of the core are interchanged with natural fuel assemblies from the center of the core. The process of switching elements within the core does not require the use of the coffin. The elements are raised and the entire mechanism turned on the rotating loading plug until the element is brought over the new position. This rearrangement within the core increased the reactivity by 0.76%. With this core revision, it is possible to operate the reactor at 61.7 megawatts. The current high-power tests are limited to this point due to full capacity operation of both feedwater pumps. These high-power densities, previously believed to be unobtainable, were reached with safety and stability in this natural circulation boiling water reactor. As a result of these engineering efforts, with Argonne National Laboratory's Experimental Boiling Water Reactor, a reasonable cost per electrical kilowatt capacity has now been established for a nuclear power plant of this type.